I would like to welcome on stage Andrea. Andrea, I just was introduced by my colleague, but he's doing a very good work on very low level of the hardware, but let him explain what is he doing. All right, let's welcome him.
Thank you. Yeah, slides are all working. So hello, thanks for the introduction, Bibi. And so I'm Andrea Di Dio. I'm actually working as a PhD student in Amsterdam in a group called VUSec. And you've had a lot of talks on software side of things in these few days. And today I'm actually going to talk on how you can exploit hardware from software. And specifically, we're going to talk about Rowhammer. So a bit of background on who I am and what I do. So as I said, PhD candidate at VUSec, and I'm mostly interested in both the offensive and defensive side of things in the hardware-software boundary. So this includes a lot of operating system stuff and a lot of basically hardware side of things, but still from software. And in fact, I've worked almost 4 years on Rowhammer itself, which is what I'm going to present today. And recently I published a paper on basically how you can defend systems, so existing systems from Rowhammer. So you can find me on Twitter, X, whatever you want to call it nowadays. And then I have also a pretty outdated blog, but you can check it out if you want. So today I want to start the presentation with basically a quote that was said by probably every kindergarten teacher ever, and it's sharing is caring. But hopefully by the end of this talk, I'll convince you of the right opposite, and why sharing, especially in the context of security, is in fact not caring. So sharing resources between processes and applications can provide a good failure mechanism. So a bit about why am I talking about Rowhammer? I said basically it's almost a decade old. So this first paper that explained the phenomena came out in 2014. And it was just showcasing how basically by accessing memory with certain patterns, you could basically force disturbance errors in memory. But since then, there's been a lot of attention for Rowhammer. So the first exploit, then Rowhammer went also on mobile, then over the network, and of course on also systems with ECC. So ECC was once thought to be basically very good protection against these spurious bit flips, but it's not good enough for Rowhammer. And then we also have a lot of coverage on newer memory modules. So this started with DDR3 memory modules, but DDR4 systems are just as vulnerable with a few tricks. So before we get into the meat of the presentation, this is basically what I'm going to be talking about. I'm going to convince you that Rowhammer is still a very powerful attack almost 10 years later. And we're going to go and walk through the explanation for like a full exploit work chain. In this case, what we're targeting is co-hosted VMs. So I think like many people nowadays store their binaries, their data on co-hosted VMs. And we're going to exploit these co-hosted VM by using page deduplication for memory massaging. So you've heard maybe of the term of memory massaging in the software context. When we're talking about hardware, it's slightly different. But we're going to go through this. And then we're going to complete the attack, we're going to do opcode flipping on the pseudo binary to achieve privilege escalation. And this is how I've structured the exploit work chain. So we're going to start with a bit about what DRAM is and how we can exploit and reverse engineer some DRAM characteristics via timing side channels, because in fact DRAM is a shared resource. Then we're going to walk through basically Rowhammer and templating. Then we're going to go through opcode flipping and page deduplication. And at the end of this, I have a short demo video to showcase the attack. So DRAM can be logically viewed, or at least a DRAM bank can be logically viewed as a matrix of cells. So you can see the diagram there on the right. And every cell is just composed by simply a transistor and a capacitor. And it stores 1 bit of data. So simple enough. And every bank has this shared resource, which is called the row buffer. And the row buffer acts somewhat like a cache for DRAM. And when we access memory, so we have a load or a store in memory, so this entails that the memory controller is actually going to activate a row. So in DRAM terms, a row activation is basically when we have to access a specific row in memory. And because DRAM is volatile, you also have a so-called refresh period. So every 64 milliseconds, typically, the memory controller will issue a periodic refresh of all the data in order to maintain data integrity. And in fact, so the memory controller sits within the CPU. So that's linked to basically whatever system you're running on, and it implements stuff a bit differently. But say we want to read row 1 in this case, or we want to read some data that's in row 1. What the memory controller is going to do is it's going to activate this row. And an activation causes the original data to be copied in the row buffer. And notice that this is a destructive operation. So the original data is not retained in the original row, but it's only going to be stored in this basically per bank cache known as the row buffer. And the data is then returned and fed back to the CPU via this row buffer. Now, of course, this row buffer is only holds a single row, and it does so per bank. So we need, kind of like we do with caches in CPUs, we need some way of replacing that row in the row buffer. And there's, of course, different policies. So as you have in cache, you have LRU, pseudo LRU, and so on and so on. We need to find some good way of saying, okay, when can we restore the data into the original row? And this operation is known as closing a row, or in DRAM terms, this is a pre-charge. So that's basically the command that the memory controller will issue. So there are 3 main types of row buffer policies. These are open row, closed row, and adaptive. So open row policy wants to postpone the pre-charge as much as possible because it thinks that you will soon access the same row in memory. So up until you don't have to activate a new row, then the first row will still be in the row buffer and will be kept there. Then closed row policy is the exact opposite. So straight after we return the data to the CPU, we pre-charge that row. And adaptive is sort of a who knows, is somewhere in between, because it's usually undocumented, and you can sort of train the memory controller to do what you want it to do. But for simplicity, throughout this talk, I'm going to assume open row policy. And so we also have to know how to address DRAM, and how does the CPU address DRAM? Because in software, even in Ring 0 at the operating system level, we only know about virtual and physical addresses. So we need a way, if we're trying to reach DRAM, we need to find a way to address these rows. And what the memory controller does is, again, undocumented, but we can reverse engineer that, and I'll show you how soon. But it will pick some bits in the physical address, and then there's like a complex XOR function that basically maps some bits to a specific DRAM address. DRAM address, you can see there is a hex tuple, so it includes a channel, which is what connects the CPU to DRAM. DIMM, so that's the physical memory stick or memory module. A rank, which is basically which side of the memory module you're on. And then what we're actually interested in, which is a bank and column and row. So we can, as I said, recover these functions via timing side channels. Because often when you have a shared resource like we do with the row buffer, there can be some information to be taken away via timing side channels or power side channels or whatever. So how can we do this? In essence, it's pretty simple. So what we want to do is we want to map a very large buffer, and this very large buffer has to be a huge page. So it can be either 2 megabyte page or a 1 gigabyte page. And what you see is that basically, if you have a huge page, because of how huge pages are mapped in the page table hierarchy, you're going to share some bits between the virtual and the physical address. So in the case of 2 megabyte pages, those are 21 bits. And in the case of 1 gig pages, we share the lowest order 30 bits. Now, 1 gig pages are not really always available. So we have to basically do what we can with the 2 megabyte pages, which are always available in modern operating systems. And that's also because we want to optimize for TLB entries as an operating system, right? So whenever the operating system sees 512 consecutive 4 kilobyte pages, it will actually merge them into a single huge page for you. So now that we share some bits, we can, in fact, have control over bits on the physical address from user space, which is, of course, usually something that you don't have. So what we want to do is we allocate a pool of probe addresses, and these are just basically random addresses that we pick at random offset within our big buffer. What we also want to do is have a base address. So this will remain constant for the entire experiment. And this is also just a random offset within our huge page. And finally, what we do is we iterate over all our pool of probe addresses. And we want to time basically the amount it takes to read from a specific row in memory. So we still don't have a notion of rows, but we know that if we have enough physical addresses and we time the access to those compared to the base address, we're going to find some bank conflicts. And the important thing about this time access function, I hope this is still readable. I know there's a bit of code, but should be readable. So what we want to do is we basically iterate through these addresses, and we do it for each pair of addresses, for each base and probe address pair. We want to iterate through a few rounds. That's just to eliminate the noise. That happens quite a lot when you're working with the side channel, so you want to minimize the noise. And then what we do is we take the timestamp counter from the CPU, access these two, dereference these two pointers, which will cause an access to memory. Take the timestamp counter again, then we have this time measurements array, again, just for noise elimination. And the most important thing here is those 4 instructions at the bottom. So I've put them there as functions, but you can inline them and do whatever you want. And these are the L fence, the CL flashes, and the M fence. So the memory fences are there in order to have serialization. So we want the order of our requests to be exactly the one that we have in our code. And the CL flash is actually the most important one because we need to reach DRAM if we're trying to see if there's a timing side channel from the row buffer. And the only way to reach DRAM is to flush the cache of where that address is stored. Because the CPU will, of course, for performance reason, if you keep accessing the same pointers, then it will cache them. And so if you do that for basically long enough, what you see is, so maybe the axes are a bit unreadable, but we have time in clock cycles on the x-axis. And then on the y-axis, we just have number of occurrences. So how many times did we see that time measurement? So all the addresses on the left of the red dotted line are addresses that are non-conflicting. So what does that mean? That means they either map to different banks or they map to the same row. Whereas, and those are basically around 200, 300 CPU cycles, at least on the system this was tested on. On the other hand, all the addresses on the right of that dotted line take a lot more time. And remember, so I was talking about the open row policy. This is because these are conflicting addresses. What that means is they map to different rows in the same bank. So the memory controller will first have to pre-charge the old row and then activate the new row. And that, of course, takes much longer. And once we have this, we basically have recovered the important bits for addressing DRAM. And this is where I have to cut a bit short, because I think I would need the whole 45 minutes to go to how to totally reverse engineer the functions. But this is a good, I think, stopping point where we know basically which bits are useful to address DRAM. So now that we can address DRAM at a row granularity, I guess the slides disappeared. Yeah, OK. We can basically now talk about Rowhammer and what templating is, at least in the context of Rowhammer. So there are three main steps to any given Rowhammer attack, and these are memory templating, memory massaging, and then the rapid hammering phase, which is where you actually trigger the vulnerability. And I'm going to go through these and give you an example of how you can do both templating and memory massaging. But in essence, Rowhammer is fairly simple. So if we manage to have repeated row activations in the same bank, this will cause basically an electrical interference with nearby rows. And this electrical interference then translates into single bit flips in adjacent or nearby rows. And notice that these bit flips are actually very deterministic and reproducible. So if a bit has flipped previously in that memory location, with a high confidence, you can say that it will flip again if you trigger with the same pattern, Rowhammer. And so both directions are also possible. So you can both go from a 1 to a 0 and from a 0 to a 1. That's not a problem. And the hammering pattern, so the amount of rows that you have to access and activate, highly depends on the DDR version that the system is running on. So for DDR3, for example, there was a so-called single-sided and double-sided Rowhammer. So that means you have two rows that you use as aggressor rows, and those flip bits in adjacent rows known as victim rows. Whereas for DDR4, instead, you need, because of the defenses employed by hardware vendors, you actually need to use a lot more rows. So again, the correct amount really depends on the system you're running from, but they vary between 4 aggressor rows to, let's say, 10, 12 aggressor rows. And so what does this look like in code? Well, it's actually super simple. Once you manage to address rows, what you do is you have a pool of aggressor rows, so n aggressor rows, and you want to activate those rows. And again, we have a CL flash call in order to reach DRAM. And visually, this is also pretty simple. So if we take the, OK. OK, there we go. Yeah, OK. So we want to basically activate these rows in memory, so our aggressor rows. In this example, we have row 0 to 4 and 6. And if we do that quickly enough, basically what happens is we're going to end with a bit flip in a nearby row. So in this case, in row 5, we had a change from a 1 to a 0 in the second cell. And a bit about templating. So you can cause bit flips everywhere in memory, but of course, not every bit flip can be useful to you as an attacker, right? You need to be able to flip a bit in the correct location in memory. And these useful bit flips are called templates, and basically they are a combination of whatever page frame number, and you need to have an offset in a page and see which bit has flipped at that particular word. And now we can go on to opcode flipping and how we can basically flip bits into opcodes. So this is based on x86 because x86 has a super dense instruction set. So what you see with x86 is that if you manage to flip a bit in any given opcode, with a very high chance, you're going to yield another valid opcode. So that at least basically gets us rid of general protection faults and stuff like that, so we don't crash the binary that we're trying to target. Bit of lag, or there we go. So as an example, I have this toy example of a very safe login program, as you can see. So the password is hard-coded to be secret. Again, very safe password. And what it does is very simple, but of course it's because it fits easily on a slide. And what it does is it takes an argument from the command line and checks against this secret password. So if the password is secret, then we get a login success. Whereas if we pass it whatever garbage value we want, we get a login failed. But to look at, we have to look at the disassembly, though, to think about how we can flip these opcodes to essentially invert program behavior, right? So we don't know the password. We don't know that the password is secret. But what we do know is that if we manage to flip a bit at the correct offset, what happens is that we can basically feed it any password. This is a bit annoying now, but so we can basically feed it any given garbage password, and we will have a login success. So in this case, what we're really looking at is that line of the disassembly there. So that means that at offset hex 199, we have this jump not equal instruction. And that basically defines our login program. So it's the check to see where to jump if the password is correct or not correct. Now, what we can do is we can flip the lowest order bit. And if we flip the lowest order bit, we go from hex 7507 to encode that particular instruction to hex 7407, which essentially inverts this opcode. So now the new behavior is whenever we provided the correct password, we get a login failed, whereas whatever garbage value gives us login success. And so I also introduced basically these templates. And how does a template look like in this case? So what we want to find is a location in memory. So this is in DRAM, where given a page frame number at offset hex 199, we can flip the lowest order bit of that specific byte. And if we do that, we know that we can land a code page there with the same characteristics as the login binary. And we can essentially invert the behavior of that program. Of course, this is all fun and games, but hey, who implements a login binary like that, right? Like, that's super unsafe. So what do we have to look at? We have to take some real targets. And a good real-world target for this type of attack is set UID binaries. So maybe I forgot to mention, I'm assuming we're running on Linux in this particular talk. And basically, these set UID binaries, such as, for example, sudo to get super user privileges, map in this sudoers.so library. And that library is the library that contains the code for the password check. So what we do is we do binary analysis, like you've seen in also a lot of previous talks during these 2 days, to discover which opcodes can be interesting. So given an opcode, which opcode can we flip a bit in? That yields basically an opposite opcode so that we can invert the password check. So in fact, our goal is to invert program behavior for binaries using sudoers.so, just like we did for the login program. This is all, again, nice, but how are we going to land a given code page, so sudoers.so, in that vulnerable location in memory, so where we have our template? And this is where memory massaging comes in. So because you know that the bit flips are reproducible, you really want that code page to land at that address in physical memory. So what we're going to use for memory massaging is something that's available on most modern operating systems, and this is page deduplication. So on Linux, this is known as KSM, or kernel same page merging. And what it does is very simple. So it has a kernel daemon called KSMD, and it scans all of physical memory for pages that have identical content. And once it finds these pages with identical content, it will merge them together. So this is, of course, to optimize for memory entries. So you don't want loads of copies lying around with the same data. How the operating system does this is it maps that page as read-only in the address space for every process that maps in that same page with so-called cow semantics, copy on write. So that means that whenever a process wants to then write to that page, it will unmerge the pages, reallocate a new page, and then map it as read-write in the address space, in the page table entries, basically, for that particular process. And visually, this is pretty simple. So what you have is you have the two co-hosted VMs. So as I said, these run on the same host operating system. And they also share basically the same hardware underlying the operating system. And in this case, we're talking about memory. So what happens is the victim virtual machine maps whatever code page it wants. This will be mapped also in the host physical memory. Now, what we can do as an attacker is map the exact same page at the location we know is vulnerable in memory. And once we do that and we wait for, again, that depends on the system, but for the daemon to scan the entire physical memory, so typically it's like every 30 seconds if you don't have too many gigabytes of RAM, what will happen is that KSMD will, in fact, merge our pages. And we are basically guaranteed, so because Linux is open source, so we can go through the memory management subsystem code quite easily, even though it's sometimes a bit of a nasty code to read. But what we know is that KSMD will actually merge these pages on the newly allocated page. So we're basically guaranteed that the victim page will be mapped at the location where we allocate, as an attacker, the page in host physical memory. There is a caveat to all this, and that's that basically KSMD doesn't work well with huge pages. So whenever KSMD scans entire physical memory and finds 4 kilobyte chunks with the same data, it will split up the huge page and then merge the pages. Now, we really need huge pages because huge pages, as I said, give us that addressing property where we can control the physical address bits. And not only that, but often aggressor rows have a striped pattern. So you want the aggressor row data to be the exact opposite of the victim row data to have a higher chance of flipping the bit. But in this case, if we let KSM do its job, what will happen is we won't have access to our aggressor rows anymore because our aggressor rows will be merged. So in this case, we use 2 aggressor rows for just to simplify. And while we're basically doing our attack, what will happen is that KSM will, in fact, merge our aggressor rows. And this will essentially nullify our exploit. So what we do is actually very easy and straightforward. We need to add some entropy to every page that we use in our aggressor rows. And yeah, so you can use 4 bytes, 8 bytes, depending on how safe you want to be. And that should be enough to basically guarantee that we keep our huge page and we keep addressing the rows that we want to address. So that's the theoretical part of the talk. Now I have a video, so unfortunately I can't do a live demo of this. mainly because the templating phase can take a very long time, and I wouldn't have time to go through it all, basically. But I do have a video which hopefully plays and is... Yeah, okay, so the terminals are also labeled to make it easier to understand, but basically what we want to concentrate on is the attacker VM. So in the attacker VM right now, what we're doing is we're going through the templating stage. So we are scanning all of physical memory for bit flips. And we know, because we've already reverse engineered and looked at the sudoers.so binary, so we know what template we're looking for. We know the exact memory location where we need a bit flip. So now it's just a matter of seeing if we can flip a bit in that particular location. And so just for completeness and for clarity, I added the host OS KVM stats. So those basically show you how KSMD is basically merging the pages in the host physical memory. And then I also added a page map terminal. So of course, usually you don't have access to that because you need to have super user rights. But for the context of the talk, I thought it would make it clear. So there you're going to see how the physical addresses of the sudoers.so page are going to be equal, even though they're mapped by two different processes. So what we're going to do now is, well, keep on scanning physical memory for these vulnerable bit flips and locations in memory. And once we're done and we find our template, what we want to do is we want to map sudoers.so in memory. And once we've mapped that, and of course, in this case, I've done it a bit differently just to showcase that the physical addresses will be the same. At some point, the victim VM will run sudo, because even for updates, right, sudo is a very common binary, and you're going to have a victim VM run that binary at some point. So basically, what we do is we play a waiting game. So maybe I can fast forward a bit to where the templating phase ends, which is around here. So now we've found our template. And what we do is, in fact, in the page map terminal, maybe it's, I should have zoomed in a bit on, on the text, but you'll see that we have two virtual addresses, and these virtual addresses map to sudoers.so. And what I'm going to do there is just check to see what the physical address is. So in Linux, you have this page map special file in the proc file system, which gives you basically the mapping of the virtual to physical addresses. So right now, maybe not very clear, but we have two different physical addresses. And now we have, again, a bit of a waiting game. So we have to let KSM do its job. And by doing its job, it literally means waiting for whatever KSM needs to basically merge those pages. So again, if we fast forward a bit, what we do now is we run the sudo binary on the victim VM. And again, we have to wait for KSM to finish its scans. So if we go around here, what we want to do now is the so-called rapid hammering stage. So we've seen that a bit has flipped there before. So we have our template. And now what we want to do is basically hammer those rows again in memory. And if we're lucky, you'll see in the victim VM now, if we run sudo, sudo su to get root access, we can get root access without any password, basically. So we have officially inverted the check. So now that this is done, I'd like to thank you for your time. And of course, if you have any questions now or later, feel free.
Let's start with the questions from the audience, if there's any. Okay. While the audience is still doing memory massaging on trying to understand the bit flips, so because your work, and I read your paper, is more on defense. So give a quick view on how do you propose defense to be implemented, and how realistic that is to be actually done by the hardware vendors or software vendors?
Yeah, so the defensive landscape for Rowhammer is a bit chaotic. So throughout the years, there has been multiple attempts at doing spot mitigations, and those never really work. But there is a big problem with defending from Rowhammer, and that is that Rowhammer is inherently a hardware issue. So we need to wait to see when hardware vendors can basically have a fix. The problem is, the manufacturing pipeline of new hardware takes few years, up to 5 years, I would say. And before clients actually manage to change and update their systems to a newer memory module, that also takes a few years of time. So that's why these hardware issues, including for attacks like transit execution attacks, these are very hard to fix. What we can do in software, and this is what I've done, is have some sort of hybrid defense. So what you do is, for example, for ECC systems, what you get, you always get an interrupt when ECC corrects the bit flip. So what you want to do is, for example, offline the vulnerable page where there has been a bit flip.
Right, and as I understood, you have proposed a Linux kernel patch to address this issue, right?
Yeah.
But it's not been merged into the mainstream.
Before it gets to mainline, if ever, there's a lot of work to do. But it's now in the development tree of one of the kernel maintainers. So we did seek for adoption, and we'll see how that goes. Hopefully, well.
So right. Although this prevalently, that is the hardware issue, as you mentioned, we can do spot mitigations through the software. You have offered the help on the Linux kernel. Let's see how it goes. Windows, do you know if there's any work on that one? Is Microsoft working on it, or that's just a black box for now?
Not that we know. So what they do is, again, for example, the fact that you can use KSM as page deduplication actually forced Windows to disable page deduplication. So that removes definitely like an arrow in the quiver of the attacker, but it doesn't solve the issue. So that's one instance of memory massaging, but then you have plenty of other ways. So just like you do with heap vulnerabilities, for example, you can do memory spraying, and because the physical frame allocator is pretty predictable in where it's going to hand out a page, if you force it into a corner, it will give you still the page you want. Yeah,
in exploit development, it's called memory grooming. Here you call it memory massaging. Has anyone already come up with a question? No. All right. While we still have time. So you mentioned, in your example, you went for the x86. You said it's very dense. That's correct. And the Rowhammer attacks have been conducted also against mobile systems, which are predominantly ARM architecture based. Is there any difference? What's the difference? It takes more time? Does it take more time to kind of do the templating? What is the key difference here?
So there is a big difference, and that is there's no direct way to flush a cache line in ARM. So what you do is, and you can do that, so actually x86, one of the things that were proposed also for x86 systems was to make CLFlush a privileged instruction so that not any user can just run CLFlush. But of course, that also doesn't really hurt the attacker that much, because what we can do is we can have cache eviction schemes. So we can reverse engineer the cache replacement policy in caches, and that's how we do it on ARM, basically, and force basically the hardware to evict our aggressor rows from the cache.
All right, I'm going to pick one question from the Menti. I'm glad. This is a good question. DDR3 and DDR4, this is what you've mentioned. So the question here is, what about DDR5?
Yeah, so who knows? So JDEC, which is basically the organization who does these standards for double data refresh, have proposed a defense called RFM. So I think it stands for refresh frequency mechanism or something like that, or management. And So that's the next defense in hardware proposed by the memory vendors. There is, as far as I know, like some work already trying to break DDR5 systems, and this is just me speculating, but it's just a matter of time. I think before it might be there might be an exploit also on DDR5 systems, because of course these hardware defenses have to be super performant, and usually you have like in economics where you have demand and supply. For computers, it's usually performance security. So of course you can't put like a super safe mitigation if you want DRAM to still remain very performant, and we don't want a load or a store to DRAM to take as much as it takes to write to disk, for example, right? That would be detrimental, and people would lose lots of money just from that loss of performance.
In your example, the example that you had on the video was about 7 minutes or so. Maybe it was sped up, I don't know. But obviously that you said there are multiple phases. The first phase is the memory templating, where you try to identify where the bit flips will happen. However, this memory templating will be unique to that particular system, to that particular layout, hardware. So if I memory template that particular system, I can then later reinitiate the attack very easy.
Yes.
Does it matter if it's not a software problem, it's a hardware problem? So it means even if it's rebooted, it doesn't matter, the problem doesn't go away, the template still stays as it is.
Yeah, indeed. So this is really linked to how the chip on die looks in memory. And in fact, if I take the same memory module, the same at least model of memory module, but by two different ones of the same model, you might have different templates actually. Right. So templating is a part of the attack that you always have to do over and over again. But of course, once you've done it once on a system, then you can basically, we call them flip tables. So you can dump to a CSV file or whatever, all these vulnerable locations, and you know that those are going to flip again with a very high chance.
So I would guess that the dominant, when you said sharing, is not caring. So most likely when we talk about the shared hosting services, if something that the hypervisor level or the base level flips, then what could be what can happen? What's the worst case scenario you can figure out?
There's a lot of worst case scenarios.
Pick one, your favorite.
I think so. I think the favorite one is what I presented I think today. But of course you can really flip bits anywhere you want. Of course, the goal usually is to achieve privilege escalation. So flipping bits in binaries is actually super nice. But think about how, for example, public key cryptography is set up. The only reason why it's very safe is it uses prime numbers to build up the keys. What if I flip a bit in a key, right? I basically, with a high chance, lose that prime property that makes up a private public key setup. So then you can crack that key much more in a much easier way. And again, then there's identification, basically theft. So you can do that as well.
All right. With this, we end the. Oh, there is a question. There you go. I was giving the last look.
So if I got you right, if we care about security, we should skip using cloud, at least for now. Is it equally applicable to all the cloud offerings, IaaS, PaaS, SaaS, or there are some differences?
So there's no fundamental differences on which type of cloud you use, because at the end of the day, the hardware is always the same. What we should stop doing, I guess, is sharing, these resources. So, but then, of course, you lose the attractive part of cloud, right? The cloud is there because you can run multiple systems on the same hardware. So it's hard to see where what the sweet spot is in this case. So again, cloud vendors as well, what they did were they turned off memory deduplication for this particular attack. But it's always a cat and mouse game if we keep going like that. It's always, spot mitigation A, exploit A, and so on and so on. At least it has been like that for almost 10 years now.
All right. With this, let's thank Andrea for the talk.
Thank you.
Get the coin and a candy.
Thanks.